Hello, and welcome back to the course on Physics for Engineers. So we are now on the 12th chapter of this course, which will talk about DC circuits or direct current circuits. So before we start our first lesson, let us first review some of the concepts that we need for this lesson. So in the previous lesson, we have discussed about the electric charge Q. And we also have discussed about the potential difference or voltage, which is just the difference between the electric potential between 2 points, say A and B. Now, for this lesson, we will be talking about current, resistance, EMF, and Ohm's law. So in this first lesson for chapter 12, we will be defining first the essential terms that we need in order to analyze a DC circuit. So let's first define current. So what is current? So current is basically the stream or the flow of charges, or basically a moving charge. So if you have a moving charge, then you can call that a current. So it can be a movement of positive charges, or it can be a motion of negative charges, or both. So more technically, current is defined as the measure of how much charge is flowing per unit time through a certain cross-sectional area of a material. So it's basically the derivative of charge per unit time. So the time rate of change of the charge. So from here, you will see that the unit for current is coulomb per second. So basically, the higher the current, the larger the current, the more charge Q is flowing per second or per unit time. So if you have a 2 ampere current, that's actually twice more charges flowing per second. So by the way, the standard unit for current is the ampere, and 1 ampere is 1 coulomb per second. So the unit coulomb, so for charge and time, charge per unit time is coulomb per second. That is defined as the unit called ampere. So 2 amperes is basically twice more charges flowing per second as compared to 1 ampere. So from here, we can actually redefine the unit for charge, coulomb. So from here, if you cross multiply the second or the time, 1 coulomb is equal to 1 ampere second. And if you take a prefix milli for ampere, such as it becomes milliampere, and if you change the unit from seconds to hours, then you have milliampere hour. So that's actually the common unit for electric charge, the layman unit for electric charge. So that is the common unit for charge that we see in our power banks and batteries. So if you have a 10 milliampere hour power bank or 20,000 milliampere hour power bank, you're actually talking about the charge in terms of milliampere hour. Okay. So in our discussion for this chapter, we will only use the conventional current. It is the current which is a flow of positive charges. So we will use this in analyzing our electrical circuits. So if you have a circuit, say a simple circuit, a light bulb connected to a battery, then we will assume that the current flowing through this circuit is the conventional current, the green one. So the green one comes out of the positive terminal of the battery and goes inside the battery through the negative terminal. So that is the conventional current. But in reality, in an actual circuit, it's actually the electron current that flows in the circuit. So this is the actual current in circuits, and it flows opposite the direction of the conventional current. So the electron current, it flows, since this is a flow of electrons, flow of negative charges, it flows in the opposite direction. But since this the electrical engineers, the electricians already use this convention that the current flowing in a circuit is the conventional current, then we'll just use the convention. So blame the electrical engineers for this. So we cannot go away now with the convention or the tradition or the convention, because this is now widely used by many people, even scientists and engineers. So we'll just follow the convention. Anyway, it's basically just the same, but opposite in directions. Again, the actual current that flows in a circuit is the electron current. We also have what we call ionic currents, the flow of ions, say anions for positive ions, or negative ions, and cations for positive ions. And this usually found in chemical solutions such as batteries. So such in batteries, in your cell phone batteries, it usually has lithium plus ions. So the lithium plus ions actually flow flow back and forth from the positive to negative terminal in your batteries. So that's how ionic current. Ionic current is usually inside the battery. The current inside the battery is usually ionic, but in a circuit, it's conventional or electron current. So there are also two categorization of current based on their direction. We have direct current or DC. It flows only in one direction. So this is the current generated by batteries. So the current generated by batteries is usually direct current. As opposed to alternating current or AC, it continuously flips or reverses direction. It is the current output from our electrical outlets. So AC. So if you connect your electric device to a battery, then the current flowing out from the battery is a direct current. It only flows in one direction. But if you plug your appliances in our outlets, that is what we call alternating current. So alternating meaning it continuously reverses direction many times in 1 second. Actually, the frequency of change in the Philippines is 60 hertz, meaning the current continually flips back and forth into a back and forth direction, clockwise, counterclockwise, 60 times in 1 second. So that one. So if you want to know more why there are two types of current, you just read some books or watch another YouTube videos regarding AC versus DC. So in this chapter, we'll only focus on DC or direct current circuits. Okay, let's now define another term that we need in order to analyze DC circuits. And this is the concept of resistivity and resistance. So resistivity, with symbol rho, Greek's letter rho, is a property of a material that resists the flow of current. So the SI unit is ohm meter. So ohm, it's a Greek letter, ohm, and then meters. Ohm times meters. That's the SI unit for resistivity. So materials can be categorized based on their resistivities as conductors, semiconductors, or insulators. So conductors have very small resistivities. If you will notice, if you have silver, it's 1.47 times 10 to the negative 8. So that's negative 8, 10 to the negative 8 ohm meter. So those are actually very small. If you have insulators have very large resistivities. So glass has can have resistivities up to 10 to the 14. Wood can have resistivities up to 10 to the 11. So, and then you have the in-between, semiconductors. Semiconductors have resistivities in between insulators and conductors. Okay, sorry. So all materials with the same material will have the same resistivity. So if you have a gold wire or a gold ball or a gold sheet, those have the same resistivity. The resistivity is 2.44 times 10 to the negative 8. Okay. This is the difference of the resistivity with temperature. A conductor has basically small resistivities at low temperature, but if you increase the temperature of the conductor of a metal, for instance, then its resistivity will increase. If its resistivity will increase, then it will not become a good conductor. It will actually become like an insulator because its resistivity is increasing with temperature. That is why in very high temperature operations such as in computer chips of your cell phones or your personal computers, uh, we use semiconductors, and the most popular semiconductor is silicon. So if you have a semiconductor, it's actually an insulator at very low temperature. So it has a very high resistivity at low temperature. But as you increase the temperature, its resistivity decreases and it becomes a conductor. So that is why if you require high temperature operations, so you must use semiconductors such as silicon. There's another phenomenon for conductors wherein if you further decrease the temperature of a conductor, there will come a time or there will come a critical temperature in which its resistivity drops to zero. When its resistivity drops to zero, then it will no longer have any resistivity. It will no longer resist any flow of current, and it becomes a super conductor. So the dream for physicists, electrical engineers, and the like is to obtain a room temperature semiconductor. As of now, superconductivity happens at very low temperature. So if we can create a superconductor at room temperature, then our energy and the price of electrical energy, will significantly drop down. Okay. So there's another concept related to resistivity, and it's what we call resistance with symbol R, capital R. It's a property of material, still the same with resistivity, property of a material to resist the flow of current, but you now take into consideration its shape and size of the material. So the SI unit is ohm. So the ohm is actually the unit for SI unit for resistance. So the resistance is basically depends on the resistivity, the length of the material, and the cross-sectional area of the material. So if you will notice, the higher the resistivity, the higher the resistance. The higher the length of the material, the longer the length of the material, the higher the resistance. The higher the cross-sectional area of the material, the smaller the resistance, since this is inversely proportional. So all gold materials have the same resistivity, but a gold wire has a different resistance than a gold sheet because they have a different shape, they have different lengths, they have different cross-sectional area. So take note of that. All materials, all gold, all gold, all materials with the same type have the same resistivity. So a gold material, a gold ball, a gold wire, and a gold sheet have the same resistivity, but they have different resistance because they now have different shapes and sizes. So if you have again a bigger resistivity, if you have then the same shape, then the bigger resistivity has the bigger resistance because this resistivity is directly proportional to R. If you have twice the area, so if the area doubles, then it's inversely proportional. So the inverse of 2 is 1/2. So half the resistance. If you have twice the length, double the length. If you double the length, then you also double the resistance. Okay, so the last term that we need to define is EMF. So it actually stands from electromotive force, but we usually don't use the full name of EMF anymore because it's quite confusing. And again, blame the electrical engineers for this convention. So it's actually an electric potential quantity. It's not a force. The electromotive force, EMF, is not a force. Again, it's not a force. It's an electric potential quantity. So its unit is not newtons because it's not a force. It is a potential quantity. So its SI unit is volt. So again, blame the electrical engineers for this, for making this convention, making this confusion. But EMF is an electric potential quantity. So the source of EMF is the source of electric potential or the source of voltage, and such as batteries. And they are responsible for current flow in a circuit. So the source of EMF can be source of voltage, so such as a battery, uh, your electrical outlet, that's a source of alternating current na EMF. If you have a battery, then that's a source of DC na EMF. So the relationship now between the concept that we have discussed earlier, the current, the resistance, and the voltage or the EMF is given by Ohm's law. Current, resistance, and voltage in a circuit. So the voltage is equal to the current times the resistance. So if you have a material and you connect the material to a source of EMF, say with voltage V, then current will flow through that material. And the relationship now is this. So the larger the EMF or the larger the voltage, the larger the current. Also, the larger the resistance, also the larger the voltage. But current is inversely, from here, current is inversely proportional to resistance. So the larger the resistance, the smaller the current, provided voltage is constant. So this is a picture depicting Ohm's law. So the voltage in volts, the resistance in ohm, and the current in amperes. So the voltage is the one responsible for current to flow in a material. So it's the one pushing the current to flow. And the purpose of the resistance is to resist the flow of current. So together, the voltage and the resistance control the flow of current. They can increase the flow of current, or they can decrease the flow of current in a material or in a circuit. So let's now have an example. So this is resistance of a copper wire. So this is a what we call a solid copper wire with wire gauge, American wire gauge number 14. And usually this has a diameter of 1.63 millimeters. And you're asked, what is the resistance of this wire? Take note, we are calculating the resistance, not the resistivity. Because we know the resistivity from the table, we know that the resistivity of copper is 1.72 times 10 to the negative 8 ohm meter. So to solve this resistance, we still need to know its length. So its length is actually given 1 meter, and its cross-sectional area, A. So this is looks like a cylinder. So its cross-sectional area is a circle. So we are given its diameter. So we can solve for the area of a circle equal to pi r squared, or pi times the diameter divided by 2 squared. But we need to convert our units to standard units. So we need to convert millimeters into meters. So milli just means divide by 1000 or multiply by 10 to the negative 3. And the divide by 2 here is to get the radius. So this is diameter over 2, then that's the radius. This is millimeter, then squared. And you get 2.56 times 10 to the negative 3 square meters, or meter squared. That's the cross-sectional area. So we can now solve for the resistance. It's resistivity times the length over the area. So this is the resistivity, this is the length, 1 meter, this is the cross-sectional area. And take note, we didn't include the units because that's fine as long as you put the final unit here, which is ohms. So take note, you should convert all of your units to standard units. As a practice, always convert your units to standard units. And then we place the final unit here, ohm. Don't forget to place the final unit. So we have 6.72 times 10 to the negative 6 ohms. So 10 to the negative 6 is basically divided by 1 million, or that is what we call micro, the prefix called micro ohms. So 6.72 micro ohms. So since the metals have very small resistivities, then it also follows that they will also have very small resistances. So 6.72 micro ohms. So metals have very small resistivity and resistance. Example number 2. So how about we connect the wire in example number 1 to a 9-volt battery. So the question now is how much current flows through the wire. So we connect this wire to the positive, one end to the positive terminal of the battery, and then the other end to the negative terminal of the 9 volts battery, and try to find the current. So current is just from Ohm's law, voltage over resistance. So the voltage is 9 volts, the resistance is 6.72 micro ohms, or times 10 to the negative 6 ohms. And then you will get 1.34 times 10 to the 6 amperes. Times 10 to the 6, that is 1 million. Basically 1.34 million amperes. And that is quite scary. So this is actually the very definition of a short circuit. So do not do this. I'm just giving you this example to show you that if you connect a wire directly to the positive and negative ends of a battery without any large resistance to control the amount of current flowing, then you will get a short circuit. So a short circuit will have a very large current, and this will cause your battery to explode, or your current or your wire to burn because of the very high current. And if you touch this wire, you might get electrocuted and you might die. So do not connect a wire direct to the terminals of a battery, and there must be a resistance large enough to control the amount of current flowing in a material. So I'm gonna show you this table, how much current can a human body withstand. So if you experience a 1 milliampere current flowing through your body, it will like be a faint tingle. 5 milliamperes, that's milli is times 10 to the negative 3, or 5 over 1000. So this is basically 1 milliampere is 0.001 ampere. 5 milliampere is 0.005 amperes. So 5 milliamperes, slight shock. 6 to 30 milliamperes, painful shock. Oh, milliamperes, that's still milliamperes. 6 to 30 milliamperes, painful shock. 50 to 150 milliamperes, extreme pain. And then 1 ampere to 4.3 amperes, this will now cause like a likely death. So 1 ampere to 4.3 amperes, death is likely. And 10 amperes, cardiac arrest and death is probable. So that one. So in our previous example, the short circuit is millions of amperes. So you will surely die if you make a short circuit and you touch the wire. So please please be careful when making your own, when working with circuits. Okay, so that's the end of this lesson, for the first lesson for the chapter on DC circuits. And I will see you again on the next lesson for chapter 12, DC circuits. So bye bye.